Hello, and welcome to The Sleepy Scientist. It's lovely to have you here. Before we begin, I'd love to know where you're watching from tonight. A quiet bedroom with the lights already low, somewhere comfortable at the end of a long day, or a familiar sofa as the evening finally winds down. Wherever you are, hopefully you're comfortable and ready to let your thoughts drift a little. If you enjoy these relaxing explorations and would like to hear more, a like and a subscription really do help this sleepy little channel keep going. And if you're already subscribed, thank you. Truly, your support means more than you might realise. Now, tonight's topic has a reputation for being dramatic. Weather is often described as loud or unpredictable. Sudden storms, strong winds, big changes in the sky. But don't worry, nothing here is meant to jolt you awake. And if it does keep you listening, at least you'll come away with a better sense of why clouds form when they do, why air moves the way it does, and why the sky is almost never as still as it looks. So, shall we begin? What is weather really? And why can it feel so chaotic, even when it's following the same simple rules it always has? The world around us usually feels steady, solid ground, air that seems calm and empty, the sky overhead quietly doing its thing. Clouds pass, wind comes and goes, rain falls then stops, but look a little closer and weather becomes something else entirely. The air above you is always moving. Heat is constantly flowing from one place to another. Water slips invisibly into the atmosphere, then returns again. None of it is random. None of it happens without reason. Over time, scientists began to understand that weather isn't a series of isolated events. It's a continuous process, a slow, planet-wide response to energy arriving from the sun. Warm air rises, cooler air sinks. Motion bends and curves, organizing itself in ways that can seem messy from the ground, but are surprisingly consistent when viewed as a whole. Weather isn't the ski misbehaving. It's the atmosphere doing exactly what physics allows it to do. In this video, we'll move gently through that process. There's no need to remember names or definitions. We'll take things slowly, one idea at a time, beginning with the air itself, then heat and motion, and gradually working toward the familiar phenomena that give weather its character: clouds, wind, rain, storms, and everything in between. So get comfortable. And with that, let's begin. Air is so familiar that it's easy to forget it is there at all. It has no obvious colour, no sharp outline, no clear boundary that says here it begins or here it ends. It fills every gap so completely that it fades into the background like silence between sounds. Because of that, air is often treated as if it were nothing, empty space, a gap waiting to be filled by more solid things. But air is not empty, and it is not nothing. Air is matter. It is made of particles with mass. Those particles take up space, they move, and they collide with one another constantly. A room full of air is not an empty room. It is crowded with countless tiny pieces, all in motion, even when everything feels perfectly still. One of the simplest ways to notice this is to pay attention to resistance. Air pushes back. It fills balloons. It presses against your skin. It slows falling leaves and softens the way sound travels. None of that would be possible if air were merely an absence. These everyday experiences are quiet evidence that the atmosphere is a physical substance, even if it rarely draws attention to itself. Air also has weight. This can feel surprising because that weight is spread evenly and gently. There is no sense of pressure in the way there is with a heavy object resting on your hand. But gravity acts on air just as reliably as it acts on stone, water, or soil. Every particle of air is pulled downward, and together they create a steady push toward the surface of the planet. Above any point on Earth, there is a tall column of air stretching upward for many miles. Each layer in that column presses on the layers below it. The air near the ground supports the weight of everything above. That constant downward push is what is meant by air pressure. It does not switch on during storms or disappear on calm days. It is always present, simply because air has mass and gravity never takes a break. This also tells something important about the atmosphere itself. It has depth. It is not a thin skin wrapped tightly around the planet, but a thick layered envelope that gradually becomes thinner with height. Near the surface, air particles are relatively close together. Higher up, they are more spread out, supporting less weight from above. There is no sharp line where air suddenly stops and space begins. Instead, the atmosphere fades gradually, layer by layer, becoming less dense as altitude increases. This gradual thinning gives the atmosphere structure. It allows different layers to behave differently, and it ensures that weather does not happen above the world, but within a deep three-dimensional body of air. Another key feature of air is that it resists motion. When something moves through air, the air pushes back. This resistance is why running into a headwind feels harder than running with the wind, and why a feather drifts rather than drops straight down. Air does not instantly move aside. It responds, but it does so gradually. The same resistance applies to the air itself. Large volumes of air do not change speed or direction quickly. They have inertia. Once air starts moving, it tends to keep moving. Once it is still, it tends to remain still until something changes the balance. Shifting the motion of air takes time and energy, especially when vast regions of the atmosphere are involved. Because of this, the atmosphere usually behaves slowly rather than abruptly. Changes unfold over minutes, hours, or days, not moments. Even when conditions change, the air adjusts at a measured pace, passing motion and energy from one part of the atmosphere to another. This slow response is one reason weather often feels gradual rather than sudden, even when the end result is noticeable. Air can also be compressed and expanded. Push it into a smaller space, and its particles are forced closer together. Let it spread out, and those particles drift farther apart. This flexibility allows air to respond smoothly to heating and cooling, rising and sinking, without breaking or snapping. It also allows the atmosphere to store energy temporarily and release it later as motion. When air is warmed, its particles move faster and spread out slightly. The same amount of air now occupies a larger volume, which makes it less dense. When air cools, particle motion slows, the air contracts, and density increases. These changes do not require dramatic shifts in temperature. Small differences are enough to matter when they occur across large areas. Because gravity is always acting, differences in density naturally lead to movement. Lighter air tends to rise through heavier air. Denser air tends to sink. This does not happen suddenly or violently. It happens slowly, guided by the surrounding air and limited by resistance. But over time, these gentle movements shape the vertical structure of the atmosphere. Even on the calmest day, air is rarely motionless in an absolute sense. At the smallest scale, air particles are always moving, colliding, and exchanging energy. What feels like stillness is simply a balance of motion, where movement in one direction is matched by movement in another. The atmosphere is always active. It is just very good at being subtle. Understanding air as a physical substance helps remove much of the mystery from weather. Weather is not something that happens to the atmosphere. It is something the atmosphere does. Air moves, spreads, rises, sinks, and resists change according to the same physical rules that govern other forms of matter. Clouds, winds, and larger weather patterns are not visitors passing through an empty sky. They are arrangements formed within a moving, layered body of air. They emerge because air has mass, responds to gravity, and changes slowly over time. Without those properties, the sky would behave in a very different way. This also explains why weather tends to have continuity. Conditions today are connected to conditions yesterday, not by coincidence, but because the air itself carries memory. Its motion, temperature, and structure reflect what has happened recently and influence what happens next. Once air is recognized as something real, with weight, depth, and resistance, the atmosphere becomes easier to picture. It is no longer an invisible void, but a vast, slowly shifting substance that surrounds the planet and responds steadily to energy and gravity. Weather happens within this substance. Every breeze, every cloud, and every larger pattern is part of the same ongoing movement of air. Nothing appears from nowhere. Nothing vanishes instantly. The sky is not a stage where events suddenly occur, but a system made of matter, always adjusting, always in motion, even when it seems quiet. With that foundation in place, the behavior of the atmosphere begins to feel intuitive. Air has substance. It has weight. It responds slowly. And everything that follows in the story of weather grows naturally out of those simple facts. All motion in the atmosphere begins with energy arriving from outside it. Not from clouds or winds or weather systems themselves, but from a steady source that rarely draws attention once it becomes familiar. The sun. Every day, sunlight travels across space and reaches Earth. By the time it arrives, it is not simply light in the everyday sense, but energy. That energy arrives continuously, quietly, and reliably, spreading across the surface of the planet. This incoming energy is what keeps the atmosphere active. Without it, air would slowly settle, temperatures would even out, and weather would lose the reason to exist. The sun does not deliver its energy evenly. That unevenness is not a complication added later, it is the starting point. Because Earth is round, sunlight strikes different parts of the planet at different angles. Near the middle of the globe, energy arrives more directly, concentrated into a smaller area. Toward the poles, the same energy is spread across a larger surface, reducing its warming effect. This geometric difference alone ensures that some regions receive more energy than others, day after day, year after year. But angle is only part of the story. What sunlight meets when it arrives matters just as much. Some of that energy falls on land, some falls on water, some is absorbed directly by the atmosphere itself. Each of these absorbs and handles energy in a different way, and those differences shape how the air above responds. Land tends to warm quickly. Sunlight strikes soil, rock, and vegetation, and much of that energy is absorbed near the surface. Temperatures can rise noticeably over the course of a single day. When the sun moves on, the same surfaces cool just as readily. This is why land areas often experience larger temperature swings between day and night. Water behaves more slowly. Oceans, seas, and large lakes absorb energy gradually, and they release it gradually as well. Heat mixes downward into the water rather than remaining concentrated at the surface. As a result, water warms and cools over much longer timescales, acting as a stabilizing influence on the atmosphere above it. Air itself absorbs some solar energy directly, but most of its warmth comes indirectly. The surface warms first, and then transfers energy upward into the air resting above it. This indirect heating slows the atmosphere's response, preventing sudden changes and allowing motion to build gradually. Because land, water, and air all respond differently, temperature contrasts appear naturally across the planet. A sandy beach warms differently from a forest. An inland plain behaves differently from a nearby coastline. A city releases stored heat differently than the countryside around it. None of this requires extreme conditions. It happens quietly, every day, simply because Earth is not uniform. Time adds another layer. Earth rotates, bringing daylight and darkness in a regular rhythm. Surfaces warm while exposed to sunlight and cool once shaded. But because different surfaces respond at different speeds, the atmosphere is always adjusting to changes that have already happened. By the time air begins to respond fully to warming, the surface below may already be cooling again. This delay matters. It prevents the atmosphere from settling into balance. Instead of reaching a steady state, it is constantly catching up, responding to yesterday's warmth, this morning's sunlight, and tonight's cooling all at once. This constant adjustment is where weather begins. Energy enters the system unevenly. Some places gain more warmth, some lose it more quickly, some store it, others release it almost immediately. These differences create imbalance, and imbalance invites motion. Energy does not remain neatly where it arrives, it spreads. Warm regions share energy with cooler ones, and the atmosphere becomes the medium through which that sharing takes place. Air begins to move, not because it has chosen to, but because uneven heating leaves it no alternative. If Earth were heated evenly, weather would be minimal. Air would have little reason to move horizontally. Large circulation patterns would struggle to form. Clouds and precipitation might still appear locally, but the broad organization of the atmosphere would be greatly reduced. Weather exists because Earth is not heated evenly, and because it never will be. Even the most familiar conditions follow this same logic. Gentle breezes develop where temperature differences are small. More persistent motion develops where contrasts are stronger or longer lasting. In every case, the underlying cause is the same. Energy has entered the system unevenly, and the atmosphere is responding. This also explains why weather often feels patterned rather than random. While the details change from day to day, the source of motion does not. The sun continues to deliver energy. The planet continues to absorb it unevenly. The atmosphere continues to adjust. Large bodies of water moderate temperatures nearby because of how they store energy. Deserts heat quickly because of how they release it. Coastlines feel different from inland regions because land and water warm and cool at different rates. These are not coincidences. They are direct consequences of how energy enters and moves through the system. Even intense conditions follow the same rules. Strong systems develop where energy has accumulated and where temperature contrast is sustained. Once that stored energy is redistributed, those systems weaken. The atmosphere does not hold on to motion longer than the imbalance that created it. There is something reassuring in this consistency. Weather is not arbitrary. It is not the atmosphere acting unpredictably. It is a system responding again and again to the same steady input of energy. The sun does not vary its behavior from one region to another. It shines steadily. What varies is how that energy is handled once it arrives. The planet's surface, with all its differences, determines how energy is absorbed, stored, and released. The atmosphere responds accordingly. Understanding this removes the sense that weather arrives without reason. Changes begin to feel earned rather than sudden. Motion becomes a consequence rather than a surprise. Energy arrives from the sun. It is absorbed unevenly. Differences appear. The atmosphere moves to redistribute what has been gained and lost. Everything that follows in the story of weather grows out of this simple sequence. The air does not invent motion. It responds to it. And that response, shaped by the uneven heating of a rotating planet, is what gives the sky its endless variety. Temperature is usually talked about as a condition. Warm or cool, comfortable or unpleasant, something checked in the morning before deciding what to wear. But in the atmosphere, temperature is not a static quality at all. It is a description of motion. At the smallest scale, air is made of tiny particles in constant movement. They are always sliding past one another, colliding, rebounding, and continuing on. Temperature describes how energetic that movement is on average. When air is warm, its particles are moving faster. When air is cool, they are moving more slowly. That is the entire definition. No extra properties are required. This matters because air is not rigid. Its particles are not locked into place. They are free to spread out, to cluster closer together, and to respond to changes in energy. When sunlight adds energy to the atmosphere, it does not sit quietly inside the air. It becomes motion almost immediately. As air warms, its particles move more quickly and push outward more strongly on their surroundings. This causes the air to expand. The same amount of air now occupies a slightly larger volume, simply because its particles are moving farther apart. Nothing has been added. The air has not gained matter. It has gained motion. Expansion changes density. Density is just a way of describing how much mass is packed into a given space. When air spreads out, the mass is distributed over a larger volume, so density decreases. Warm air is therefore less dense than cooler air nearby. Cooler air behaves differently. With less energy, its particles move more slowly. They stay closer together, and the air contracts slightly. The same mass now occupies a smaller space, so density increases. This difference does not require extreme cold. Even modest cooling can increase density enough to matter when it affects large volumes of air. These differences in density are important because the atmosphere exists under gravity. Gravity pulls more strongly on denser air than on lighter air occupying the same amount of space. When air of different densities is layered together, gravity begins to rearrange it. This rearrangement is known as buoyancy, though the idea is simpler than the word suggests. Buoyancy is what happens when lighter material is surrounded by heavier material in a gravitational field. The lighter material tends to rise. The heavier material tends to sink. The same principle allows a warm balloon to lift, or a piece of wood to float on water. In the atmosphere, buoyancy is not an added force. It is an outcome. Warm air does not rise because it is being pushed upward by temperature. It rises because the surrounding denser air presses downward more strongly, leaving upward movement as the easiest option. At the same time, cooler, denser air nearby tends to sink, sliding into the space left behind. Rising and sinking happen together. One does not occur without the other. Together they create vertical motion throughout the atmosphere. This vertical motion is unavoidable wherever temperature differences exist. As long as some air is warmer and some is cooler, the atmosphere cannot remain perfectly layered and still. Even when the sky looks calm, slow, upward, and downward movements are taking place. These movements are usually gentle. Air does not shoot upward or plunge downward dramatically. It drifts. It lifts gradually, resisted by surrounding air and slowed by its own inertia. Large changes often begin as very small motions spread across wide areas. As air rises, something else happens. The pressure around it decreases because there is less air pressing down from above. With less pressure, the rising air expands further. Expansion requires energy, and that energy comes from the motion of the particles themselves. As a result, rising air cools as it expands. This cooling does not require contact with colder air. It happens naturally as the air spreads out. The particles lose some of their speed because their energy is now shared across a larger volume. Rising air cools simply by rising. This effect helps determine how far air can continue to rise. In some cases, the air remains warmer than its surroundings even as it cools, so it keeps lifting. In other cases, it cools enough to match the density of the air around it and slows to a stop. Over time, this process helps arrange the atmosphere into layers. Sinking air experiences the opposite effect. As it descends into regions of higher pressure, it is compressed. Compression brings particles closer together and increases their motion slightly. The air warms as it sinks, not because it has gained energy from outside, but because its existing energy is concentrated into a smaller space. These warming and cooling effects help stabilize the atmosphere. They prevent air from rising or sinking endlessly. Instead, air tends to settle at levels where its density matches its surroundings, creating a layered structure that can persist for long periods. What emerges from all of this is a steady exchange between temperature and motion. Energy changes particle speed. Particle speed changes density. Density differences create vertical movement. Vertical movement changes temperature again through expansion and compression. The process loops continuously, quietly shaping the behavior of the atmosphere. This is why vertical motion is so central to weather. Clouds form where air rises and cools enough for moisture to condense. Clear skies are more common where air sinks and warms. Even when clouds are absent, vertical motion is still influencing how energy moves through the atmosphere. It also explains why weather feels three-dimensional rather than flat. Air does not only move across the surface of the planet, it is constantly moving upward and downward as well, linking the ground to higher layers of the sky. None of this requires extreme conditions. Everyday temperature differences are enough. Sunlight warming a field, shade cooling a nearby forest, water moderating the air above it. These small contrasts, repeated across the planet, keep the atmosphere in motion. Thinking of temperature as motion rather than as a fixed property helps make sense of all this. Warmth is not something air contains like a substance. It is something air is doing. Faster motion, greater spacing, lower density, a tendency to rise. Cold, by contrast, is not an active force pulling air downward. It is simply slower motion. Particles move less vigorously, stay closer together, and allow gravity to have a stronger effect. Denser air settles because nothing holds it up. There is a quiet logic to this system. The atmosphere does not need instructions or triggers. As soon as energy is unevenly distributed, motion begins. As soon as motion begins, temperature changes follow. The air adjusts continuously, guided by the same simple principles everywhere. This is the bridge between energy and movement. Sunlight delivers energy. Temperature turns that energy into motion. Density differences give that motion direction. Gravity ensures that vertical movement is always part of the response. Once temperature is understood in this way, the behavior of the atmosphere becomes easier to follow. Rising air, sinking air, layers forming and shifting over time. These are not special events. They are the natural consequences of air behaving as matter under gravity. The sky does not move because it is restless. It moves because energy becomes motion, and motion reshapes the air. That process never stops, even when everything above seems calm and unchanged. Pressure is often spoken about as if it were something added to the atmosphere, as if the sky decides to increase it in one place or release it in another. In reality, pressure is not imposed on the air at all. It forms naturally simply because air has weight, and gravity is always at work. Every point on Earth sits beneath a column of air that stretches upward for many miles. That column may not be visible, but it is always there. Each layer of air in the column presses gently on the layers below it, and together they create a steady downward force. This force is what is meant by air pressure. It exists whether the sky is clear or cloudy, whether the air is moving or still. The amount of pressure at any location depends on how much air is stacked above it. Near the surface, the column is tall and heavy, so pressure is higher. As altitude increases, the column becomes shorter. There is less air overhead, so the pressure decreases. Nothing special has to happen for this to be true. It is simply gravity acting on air with mass. Because the atmosphere has depth, pressure naturally changes with height. But pressure also changes from place to place across the surface, and those changes come from air moving vertically. When air warms, it tends to expand and rise, As it lifts, it spreads out into higher layers of the atmosphere. This does not remove air from the column below, but it does thin it slightly. With some of the air now higher up and more spread out, the total weight pressing down at the surface decreases. Pressure falls, not because anything has been pulled away, but because the air has rearranged itself. The effect does not need to be dramatic. Even slow, gentle rising over a wide area can reduce surface pressure enough to matter. The atmosphere is sensitive to these vertical shifts, and pressure responds smoothly as soon as the distribution of air changes. When air cools, the opposite happens. Cooler air becomes denser and tends to sink. As it settles downward, it adds to the column of air below. More air is now pressing down on the surface, so pressure increases. Again, nothing is being forced. Gravity simply acts on the air as it gathers. These rising and sinking motions are happening all the time. Somewhere on the planet, air is lifting. Somewhere else, air is settling. Pressure adjusts in response, increasing where air accumulates and decreasing where air thins. The atmosphere is constantly reshaping its internal balance in this way. Because air moves slowly and resists sudden change, pressure rarely shifts abruptly. It tends to evolve over time, strengthening or weakening as long as the motions that created it continue. A region of lower pressure exists as long as air keeps rising above it. When that upward motion slows, pressure gradually increases again. The same is true for higher pressure. It persists only while air continues to sink and collect. This is why pressure differences are always temporary. They form, change, and dissolve as air moves. No region remains locked into one state indefinitely, because the atmosphere never stops adjusting. As energy enters and leaves the system, air rearranges itself and pressure follows along. It helps to think of pressure as a description rather than a driver. Pressure does not tell the air what to do. It reflects what the air has already been doing. Where air has been rising, pressure tends to be lower. Where air has been sinking, pressure tends to be higher. Pressure is the record left behind by vertical motion. Horizontal differences in pressure only exist because vertical adjustments have already taken place. Warm air has lifted in one region, lightening the column below. Cooler air has settled in another, thickening the column there. The contrast between those columns appears at the surface as a pressure difference. This makes pressure feel less mysterious. It is not something separate from air, and it is not something the atmosphere creates deliberately. It is the natural outcome of air moving under gravity in response to temperature differences. Because uneven heating never stops, pressure differences never stop forming. At the same time, they never stop fading. The atmosphere is always somewhere between imbalance and adjustment, never fully settled, never completely chaotic. Even on days described as quiet or uneventful, pressure is still changing. Small vertical motions continue, often too subtle to notice directly. Instruments detect these changes long before they are obvious to the senses, but they are always present. Pressure also helps explain why the atmosphere tends to behave in a measured way, rather than all at once. Moving large amounts of air vertically takes time and energy. As a result, pressure changes usually unfold gradually, giving weather its sense of continuity. Conditions evolve instead of appearing suddenly. Seen this way, pressure is not something to worry about or anticipate. It is simply part of the background structure of the atmosphere. It exists because air exists. It changes because air moves. And it continues to adjust as long as the atmosphere remains active. Understanding pressure as something that forms naturally makes the behavior of air easier to follow. Changes no longer seem arbitrary. They follow from earlier motion, unfolding steadily as air rises, sinks, spreads, and settles. Once this idea is clear, the stage is set for understanding how air begins to move across the surface. Pressure differences do not appear out of nowhere, and they do not act alone. They arise from vertical motion, and they quietly shape how air responds next. Pressure, then, is not an extra ingredient in weather. It is the atmosphere keeping track of its own weight, moment by moment, as air continues its slow, constant rearrangement under gravity. Wind often gets treated as something separate from the air itself, as if it were an extra ingredient added to weather, arriving suddenly and making its presence known before disappearing again. In everyday language, wind is described as blowing, gusting, or battering, which can make it feel active and even aggressive. But wind is not a force acting on the atmosphere. It is the atmosphere responding. At its simplest, wind is air moving from one place to another because the balance of pressure is uneven, where there is slightly more air pressing down in one region and slightly less in a neighbouring region. Air begins to move across. It does not rush. It does not decide. It simply follows the easiest path available, drifting from higher pressure toward lower pressure. This movement is not optional. As long as a pressure difference exists, air will respond. The atmosphere is not capable of ignoring imbalance. Motion is the natural outcome. Most of the time, these pressure differences are small, so small that the resulting movement is barely noticeable, a faint breeze that brushes the skin, a gentle flow that moves leaves but not branches. These subtle winds are the most common state of the atmosphere, even if they are rarely given much attention. Gentle winds come from gentle imbalances. When the difference in pressure between two places is slight, the air adjusts slowly. The movement is calm, steady, and easy to overlook. There is nothing dramatic happening, just air redistributing itself one small step at a time. Stronger winds arise in exactly the same way. The rule does not change. The only difference is the steepness of the pressure contrast. When pressure drops more sharply from one place to another, air responds more quickly. The greater the difference, the faster the movement needed to even things out. This does not mean the air has become more energetic on its own. It means it is responding to a larger imbalance. The same process is at work, scaled up. Wind speed reflects how urgently the atmosphere needs to redistribute air, not a change in the nature of the air itself. It can help to think of pressure differences as slopes rather than switches. A gentle slope leads to a slow, easy movement. A steeper slope leads to faster motion. In both cases, the movement is a response to the shape of the landscape, not a decision made by the air. Because pressure differences are always forming and dissolving, wind is almost always present somewhere. Complete stillness is surprisingly rare. Even on days described as calm, air is often moving slowly enough to escape notice. The motion may be too gentle to feel, or it may be masked by other sensations, but it is there. If the atmosphere were ever to reach perfect balance, with pressure identical everywhere, wind would stop. But uneven heating, vertical motion, and the slow adjustment of air make that state nearly impossible to maintain. The atmosphere is always a little out of balance, and so air is always adjusting. Wind also tends to persist once it begins. Air has inertia. When it starts moving, it does not stop instantly when the pressure difference weakens. Instead, it slows gradually, easing back as conditions change. This is why breezes can linger even after the original cause has faded. This inertia contributes to the smoothness of wind. Rather than flicking on and off, wind usually strengthens or weakens over time. Sudden changes do happen, but they are far less common than gradual shifts. Most of the time, the atmosphere prefers continuity. Another reason wind often feels steady rather than chaotic is that large volumes of air are heavy. Changing their motion quickly requires significant energy. As a result, the atmosphere spreads adjustments over time and space, smoothing sharp contrasts and softening abrupt transitions. Wind is also rarely uniform. Even when air is generally moving in one direction, it does not travel as a single solid sheet. Some parts move slightly faster, others lag behind. Surface features, Temperature differences and obstacles introduce small variations, creating a textured flow rather than a rigid one. This unevenness can make wind harder to notice. Instead of one clear sensation, it arrives as a collection of subtle movements that blend into the background of everyday experience. The air is in motion, but it does not always announce itself. Because wind responds to pressure differences, it is closely tied to what the atmosphere is doing vertically as well as horizontally. Rising air in one area lowers pressure there. Sinking air elsewhere raises pressure. The horizontal movement between them is simply air redistributing itself in response to those vertical shifts. In this way, wind acts like a messenger. It carries the effects of vertical motion across the surface, linking distant regions together. By observing wind, it is possible to infer where air has been rising and where it has been settling, even without seeing those movements directly. Gentle winds often indicate small, widespread imbalances that are being resolved efficiently. Faster winds suggest sharper contrasts or more persistent differences. But in every case, the underlying process is the same. Air is moving because pressure is uneven. This perspective helps remove the sense that wind is something that arrives uninvited. It is not an external disturbance. It is part of the atmosphere's normal behavior, present whenever conditions are not perfectly balanced. Most of the time, wind does its work quietly. It moves heat from one place to another. It carries moisture. It shapes clouds. It influences temperature near the surface. All of this happens whether or not the movement is strong enough to be felt. Wind only becomes noticeable when it interacts with things that resist it. Trees sway, clothing flutters, buildings deflect the flow. These interactions draw attention to the motion, but the motion itself was already there. In open spaces far from obstacles, air can move smoothly for long periods without creating much sensation at all. It does not need to roar or gust to be effective. It can simply flow, redistributing air and energy steadily over time. Thinking of wind as a response rather than a force places it back into context. It is not an event layered on top of weather. It is one of the ways weather operates continuously in the background. Air moves because pressure is uneven. Pressure is uneven because air is rising and sinking. Rising and sinking occur because temperature varies. Each step follows naturally from the one before it. Wind sits within this chain, quietly connecting vertical motion to horizontal flow. Once this chain is understood, wind becomes easier to live with and easier to predict. Its presence, direction, and strength all reflect conditions that already exist within the atmosphere. Nothing appears without cause. Nothing moves without reason. Most of the time, that motion is gentle, a background adjustment that goes on whether it is noticed or not. Wind does not need to be dramatic to matter. It is simply air doing what air does, smoothing out differences as the atmosphere continues its slow, ongoing effort to balance itself. When air begins to move across the surface of the planet, it might seem reasonable to imagine it travelling in straight lines, from higher pressure toward lower pressure, from warmer regions toward cooler ones, direct, efficient, and uncomplicated. But the surface beneath that moving air is not still. Earth is rotating steadily and continuously. It completes one full turn each day, carrying continents, oceans, and the lower layers of the atmosphere along with it. From space, this motion is obvious. From the ground, it is almost impossible to notice because everything nearby is moving together. Air that begins to move, however, does not remain perfectly locked to the surface below. Once air starts flowing horizontally, it carries momentum from where it began. As the planet continues to rotate beneath it, that shared motion begins to drift out of alignment. This is where paths begin to curve. To understand why, it helps to think about motion over time rather than motion in a single moment. If air moves only a very short distance, the rotation of the Earth beneath it makes little difference. Over a few meters or even a few kilometers, the surface has not shifted enough to noticeably change the path, but as distance increases, the effect accumulates. Imagine air moving freely across a large stretch of the planet. While that air is travelling forward, the ground beneath it is rotating eastward. The air continues along its original direction, but the surface underneath subtly shifts sideways. To an observer standing on the rotating Earth, the air no longer appears to move in a straight line. Instead, its path seems to bend. Importantly, the air itself is not suddenly changing direction, is not being pushed sideways by an invisible hand. The apparent curve arises because the reference frame is rotating. The path looks curved only because the ground beneath is turning while the air keeps moving. This is easier to picture with familiar objects. Rolling a ball across a slowly spinning platform produces a similar effect. From above, the ball travels straight. From the platform itself, the ball appears to curve. The motion of the surface alters how the path is perceived. The same thing happens in the atmosphere. As air moves over longer distances, the rotation of the Earth beneath it becomes increasingly important. The longer the air remains in motion, and the farther it travels, the more pronounced the apparent curvature becomes. Time and distance both matter. This is why small local winds often seem to move in fairly straight lines, while large-scale flows trace broad arcs across the planet. The same physical rules apply in both cases. The difference lies in scale. Location also plays a role. Earth does not rotate at the same surface speed everywhere. Near the equator, the surface moves more quickly. Closer to the poles, that motion slows. As a result, the apparent deflection of moving air varies with latitude, becoming more noticeable where the rotational speed of the surface is greater. What emerges from this is a consistent pattern. Air still moves from higher pressure toward lower pressure, but its path is gently deflected along the way. The deflection does not cancel the motion. It reshapes it. Instead of flowing straight into regions of lower pressure, air tends to curve around them. The movement becomes a sweeping arc rather than a direct line. Over time, these curved paths organize the atmosphere into broad circulating flows. This is not something the atmosphere chooses to do. It is the natural outcome of motion occurring on a rotating planet. Once air is allowed to move freely over enough distance, straight paths quietly give way to curved ones. Because this effect builds gradually, it rarely feels abrupt. Air does not suddenly turn a corner. The curvature emerges slowly, shaping the motion more and more as time passes. This contributes to the smooth, continuous feel of large-scale wind patterns. It also helps explain why the atmosphere often appears organized rather than chaotic. Motion follows predictable paths, guided by pressure differences and shaped by rotation. Even as details change, the underlying structure remains familiar. These curved motions become especially important when air is moving persistently around regions of higher or lower pressure. Rather than rushing straight inward and stopping, the air bends, passes by, and continues moving. Over time, circulation develops, with air flowing around centers rather than directly into them. This tendency toward rotation does not require extreme conditions. It emerges naturally wherever air has time and space to move. The planet's rotation ensures that large-scale motion rarely stays linear for long. It is worth noting that rotation does not create motion in the atmosphere. Pressure differences do that. Uneven heating sets air in motion. Rising and sinking create imbalances. Rotation simply modifies how that motion unfolds once it begins. Without rotation, air would still move, but it would take more direct paths flowing straight toward areas of lower pressure. With rotation, those paths bend, and circulation becomes the dominant pattern at larger scales. Because Earth's rotation is steady and predictable, its influence on moving air is steady as well. It does not switch on or off. It does not vary from one day to the next. This consistency helps anchor the atmosphere's behaviour, even as energy input and surface conditions change. Over time, curved motion becomes the norm for large-scale winds. Flow aligns into broad paths that circle regions rather than collide with them. This reduces congestion, spreads energy more efficiently, and allows motion to persist without quickly cancelling itself out. The result is an atmosphere that redistributes heat and momentum smoothly across the planet. Air curves, adjusts and circulates, responding continuously to pressure differences while being guided by the turning world beneath it. None of this requires complex mathematics to appreciate. It follows from a simple idea. Air moves across a surface that is itself in motion. Straight paths do not remain straight when the ground below is rotating. Once this idea settles in, many features of atmospheric motion begin to feel more intuitive. Why winds follow sweeping paths. Why large systems tend to rotate. Why motion spreads out rather than collapsing inward all at once. The atmosphere is not tracing patterns at random. It is responding to uneven heating, guided by gravity and shaped by the rotation of the planet it surrounds. As air continues to move across Earth, rotation quietly bends its path, encouraging flow to curve and organize. Over distance and time, these curves become defining features of global motion. This does not mark a new force entering the story. It is simply the same air, responding to the same pressures, moving across a turning world. The complexity that emerges comes not from complicated rules, but from simple ones interacting steadily at scale. With this in mind, curved motion stops feeling like a complication and starts feeling inevitable. Once air begins to travel far enough, straight lines fade away, replaced by gentle arcs that reflect the quiet influence of Earth's rotation beneath the sky. When stepping back from individual winds and curved paths, a larger picture begins to appear. The atmosphere is not only adjusting from place to place, it is organizing itself across the entire planet. This organization begins with the simplest contrast of all. Some regions of Earth receive more energy from the sun than others. Near the equator, sunlight arrives more directly and more consistently. Toward the poles, it arrives at a lower angle and spreads over a larger area. As a result, the lower latitudes tend to gain more heat, while the higher latitudes tend to lose more than they receive. Warm air near the equator rises. Cooler air closer to the poles sinks. These two motions are not separate events. They are connected parts of a single process. When air rises in warmer regions, it cannot simply disappear upward. It must move somewhere. High above the surface, that air begins to spread out, drifting away from the region where it first lifted. As it travels, it gradually cools. Eventually, it becomes dense enough to sink again, returning toward the surface in cooler parts of the planet. This creates a loop. Air rises where energy is plentiful, travels away from that region, sinks where energy is scarcer, and then flows back along the surface to complete the circuit. These loops are slow, broad, and persistent, forming the backbone of global air circulation. They are not sharp or rigid. They are more like wide conveyor belts, constantly moving but rarely stopping. Each loop takes time to complete, often days or weeks, and the air within them is always adjusting as it goes. Because the planet is large, these loops do not exist as a single, simple pattern. Instead, they repeat. Rising and sinking zones appear in bands that circle the globe, each one shaped by latitude, rotation, and the uneven distribution of energy. Near the equator, rising air dominates. Farther away, sinking air becomes more common. Between these regions, air flows horizontally, connecting upward motion in one place with downward motion in another. Together, These motions form a repeating structure that wraps around the planet. What matters most is not the exact position of any one loop, but the fact that they exist at all. They provide a steady way for the atmosphere to move energy from where it is abundant to where it is needed. This redistribution happens slowly. Warm air does not rush poleward in a straight line. It rises, curves, spreads, cools, sinks, and returns in stages. Each step moderates the transfer of heat, preventing extreme differences from building unchecked. In this way, global circulation acts as a kind of thermostat. It does not eliminate temperature contrasts, but it softens them. Heat gained in one region is shared with others. Cold regions are not left entirely isolated. The atmosphere becomes a bridge between extremes. Because these circulation patterns are driven by persistent features of the planet, they tend to repeat. Earth's shape does not change. Its rotation remains steady. The general distribution of sunlight follows a familiar rhythm. As a result, the broad structure of atmospheric circulation remains recognizable year after year. This repetition brings stability. While local conditions can vary from day to day, the larger framework stays in place. Air continues to rise in similar regions, sink in others, and flow between them in predictable ways. The atmosphere is dynamic but not disorderly. This stability is one reason long-term climate patterns exist. Regions tend to be warmer, cooler, wetter, or drier, not by chance, but because they sit within these large-scale circulation loops. The constant movement of air shapes average conditions over time. It is also why changes in one part of the planet can influence distant regions. When air moves within these loops, it carries heat, moisture, and momentum across vast distances. A shift in energy input in one latitude can ripple outward through the circulation, subtly affecting areas far away. Despite this complexity, the system remains grounded in simple ideas. Warm air rises, cool air sinks, the planet rotates, air moves to balance differences. From these basic principles, a global pattern emerges. The atmosphere does not need to invent new behavior at larger scales. It applies the same rules repeatedly, linking local motion into planetary organization. Small movements add up, gentle flows combine. Over time, structure appears. Because these circulation loops are so large, they move slowly. Changes unfold over long periods, not moments. This slowness adds to the sense of calm in the system as a whole. Even when surface conditions shift, the deeper circulation continues, adjusting gradually rather than abruptly. This does not mean the atmosphere is frozen in place. The loops shift slightly with the seasons, responding to changes in sunlight. They expand, contract, and wander, but they do not vanish. Their presence anchors the behavior of the atmosphere across time. Keeping names and labels to a minimum helps here, because the underlying idea matters more than terminology. The atmosphere organizes itself into repeating bands of rising and sinking air. These bands connect through horizontal flow, forming loops that encircle the planet. Once this is understood, the atmosphere begins to feel less like a collection of isolated events, and more like a coordinated system. Winds in one region are connected to vertical motion elsewhere. Temperature differences are linked across latitudes. Nothing happens entirely on its own. This perspective also explains why the atmosphere can handle enormous amounts of energy without becoming chaotic. Instead of energy piling up in one place, circulation spreads it out. Instead of sharp boundaries, gradual transitions form. The system absorbs change by distributing it. Planet-scale circulation is the quiet background against which all other weather unfolds. It is always present, whether noticed or not, guiding the general flow of air around the globe. Local conditions sit within this larger framework, shaped by it but never entirely separate. Seen this way, the atmosphere is not restless or unpredictable by nature. It is methodical. It repeats patterns because the conditions that create them repeat as well. The same forces act day after day, organizing motion in familiar ways. As air continues to rise, sink, curve, and circulate, heat is slowly moved from regions of surplus to regions of deficit. The planet breathes in this rhythm, not quickly, not dramatically, but steadily. By zooming out to this scale, weather begins to feel less like a series of isolated changes and more like a continuous flow. Individual motions make sense as part of a larger circulation, one that wraps around the planet and ties everything together. This global organization does not remove variety. It provides context for it. Within these broad loops, countless local variations still occur, but they occur within a stable structure, shaped by the enduring relationship between sunlight, gravity, motion, and a rotating world. Understanding this makes the atmosphere feel both larger and calmer at the same time. Larger because its motions span the globe. Calmer because those motions follow patterns that repeat, adjust, and persist, quietly redistributing energy as the planet turns beneath the sky. High above the surface, far beyond rooftops, trees, and even most clouds, the atmosphere behaves a little differently. The air is thinner, colder, and less directly connected to the ground below. Motion still follows the same physical rules, but the balance between them begins to shift. One of the most important changes with height is temperature. Near the surface, temperatures are strongly influenced by land, water, and daily cycles of sunlight. Higher up, those influences fade. The air is less affected by what lies beneath it and more shaped by broad patterns of heating and cooling across the planet. As a result, temperature differences often become sharper with altitude. Warm regions and cool regions that may seem modest near the ground can appear far more distinct higher in the atmosphere. The air up there is less mixed by friction with the surface, allowing contrast to persist and strengthen. Where temperature differences sharpen, pressure differences sharpen as well, and where pressure differences sharpen, air responds. This leads to the formation of narrow bands of fast-moving air high above the surface. These bands are not storms or weather systems in their own right. They are persistent currents, flowing steadily along the boundaries between warmer and cooler regions aloft. Because the air is thinner at these heights, it offers less resistance to motion. Once these fast-moving currents form, they can maintain high speeds over long distances. They do not need to rush or surge. Their motion is smooth, continuous, and largely invisible from the ground. These upper-level currents are not spread evenly across the sky. They tend to organize into long, narrow paths that circle the planet. Their exact position shifts gradually with the seasons, following the slow movement of temperature boundaries below them. Although they exist far above everyday experience, these fast-moving bands play a quiet but important role in shaping what happens closer to the ground. One way to think about them is as guides rather than drivers. They do not create surface weather directly. Instead, they influence where air below can rise, sink, and move. They help steer the broad motion of the atmosphere, setting the pace and direction for changes nearer the surface. Surface air, slowed by friction with the ground, buildings, and terrain, moves much more gently. It responds to local pressure differences, heating and cooling. The air above, freer to move, responds to larger-scale contrasts and moves more swiftly. This separation creates layers. The lower atmosphere handles local detail. The upper atmosphere handles long-distance flow. They are connected, but not tightly bound. Because of this layering, changes high above can influence the surface without touching it directly. When upper-level currents shift position or strength, they can encourage rising air in some regions and suppress it in others. They can help draw air upward from below, or allow it to settle more easily. This influence is subtle. Nothing is pulled or pushed sharply. Instead, the upper flow alters the background conditions, making certain patterns more likely to develop and persist. It also helps explain why surface weather tends to move. Conditions rarely stay fixed over one location for long. As upper-level currents flow past, they carry the broader atmospheric structure with them. Regions of rising air, sinking air, and pressure differences drift along guided from above. From the ground, this movement can feel mysterious. Clouds appear, change shape, and move on. Air pressure rises and falls, but much of this motion reflects activity far overhead in layers that are never directly seen. Despite their speed, these high-altitude currents are remarkably stable. They do not wander randomly across the sky. Their paths are shaped by the same factors that organize global circulation, uneven heating, planetary rotation, and the distribution of temperature across latitudes. Because those factors change slowly, the upper-level flow changes slowly as well. Day-to-day variations occur, but the overall structure remains familiar. This stability is one reason large-scale weather patterns often feel coherent rather than chaotic. Another important feature of these fast-moving bands is that they act as boundaries. Air on one side may be warmer or colder than air on the other. These boundaries help maintain the sharp temperature contrasts that drive motion throughout the atmosphere. Near the surface, boundaries tend to blur. Friction, terrain, and mixing soften differences. Higher up, the air can maintain sharper edges, allowing energy and momentum to be transported efficiently across long distances. This separation between upper and lower layers means that not all motion is shared equally throughout the atmosphere. A strong current high above does not automatically translate into strong winds at the surface. Likewise, calm conditions below can exist beneath vigorous motion aloft. The atmosphere is layered, and each layer has its own character. This layering also adds a sense of depth to weather. What happens at the surface is influenced by what happens above, but not dictated by it alone. Local conditions still matter. Heating, cooling, and surface features all play a role. The upper flow provides context rather than control. Keeping the imagery distant helps here. These high-altitude currents are not dramatic ribbons tearing across the sky. They are quiet rivers of air, flowing far above everyday life, shaping the atmosphere through persistence rather than force. They do their work gradually, by guiding where air can rise or sink, by steering large-scale motion, and by maintaining temperature contrasts. They help determine how weather evolves over time. Understanding their role helps remove the sense that weather moves arbitrarily. Patterns shift because the larger flow shifts. Changes arrive because the broader circulation carries them along. This does not mean everything is predetermined. The atmosphere remains flexible and responsive. Small changes can grow or fade depending on local conditions, but those changes occur within a framework shaped by motion high above. From this perspective, surface weather becomes part of a layered conversation. The ground speaks through heating and cooling. The air above responds, higher layers adjust and guide. Each level influences the others without overwhelming them. Fast air high above the surface is one of the reasons weather feels connected across large distances. Conditions in one region can influence another far away, not directly, but through the slow steering of the atmosphere from above. This also explains why weather often arrives from somewhere else rather than forming in place. The atmosphere is always in motion at multiple levels, carrying patterns along paths set by global circulation and sharpened by upper-level flow. By appreciating this vertical structure, the atmosphere becomes easier to picture. It is not a single sheet of moving air, but a layered system with different speeds, roles, and influences at different heights. Near the ground, motion is gentle and shaped by the surface. Higher up, motion is faster and guided by large-scale contrasts. Together, these layers create weather that evolves smoothly, carried along by currents that are steady, distant, and quietly persistent. Fast air high above does not demand attention, it does not announce itself, but is always there, shaping the movement of the atmosphere from afar, ensuring that weather unfolds not as isolated moments, but as part of a continuous, flowing system that spans the sky. Water is familiar. It falls as rain, collects in rivers, fills oceans, and settles into clouds that drift overhead. Because it is so visible, it is easy to think of water as something that only matters once it appears. But in the atmosphere, water does much of its most important work while remaining completely unseen. In its vapor form, water is invisible. It looks exactly like dry air, and yet it is one of the most influential substances shaping how weather behaves. The story begins at the surface. Wherever liquid water is exposed to air, evaporation can occur. This process does not require boiling or dramatic heat. Individual water molecules at the surface are always moving. Some of them, by chance, gain enough energy to break free from their neighbours and drift upward into the air. When this happens, energy is absorbed. The water molecule carries that energy with it as it escapes into the atmosphere. The surface it leaves behind cools slightly because energy has been removed. This is why evaporation has a cooling effect, whether it happens from skin, soil, or the surface of the ocean. This absorbed energy does not disappear. It becomes stored within the water vapor itself. Water vapor is therefore not just a gas mixed into the air. It is a carrier of energy. Each invisible molecule holds onto the energy it absorbed during evaporation, quietly transporting it upward and outward as it moves with the air. Because oceans, lakes, rivers, and even damp ground cover much of the planet, evaporation is happening constantly. The atmosphere is always receiving water vapor, and with it, stored energy. This happens most efficiently over warm surfaces, where water molecules are already moving more energetically and can escape more easily. Warm air can hold more water vapor than cool air. As air warms, the average motion of its particles increases, creating more space for water molecules to remain mixed in without condensing. As a result, warmer regions of the atmosphere often carry more water vapor and therefore more stored energy than cooler regions. This has an important consequence. Two air masses at the same temperature can behave very differently depending on how much water vapor they contain. One may be relatively calm and stable. The other may be primed for more dramatic change simply because it carries more hidden energy. Despite this, water vapor often goes unnoticed. It has no smell, no color, and no shape. It does not announce itself until it changes state. But while it remains invisible, it is actively influencing how air moves, rises, and responds to temperature changes. The key moment comes when water vapor turns back into liquid water. As air rises, it cools. Cooler air can hold less water vapor. Eventually, the air reaches a point where it can no longer keep all of that vapor mixed in. When that happens, water molecules begin to cluster together again, forming tiny droplets. This process releases energy. The energy that was absorbed during evaporation is returned to the surrounding air when water vapor condenses. The air warms as a result, even though it may still be cooling overall due to expansion. This release of stored energy is known as latent energy, not because it is mysterious, but because it was hidden within the vapor until this moment. No equations are needed to understand the effect. Energy was taken in during evaporation. That same energy is given back during condensation. The atmosphere remembers where that energy is stored and retrieves it when conditions allow. This release of energy changes how air behaves. Rising air that contains water vapor does not cool as quickly as dry air would. The added warmth from condensation helps the air remain lighter than its surroundings, allowing it to continue rising more easily. In this way, water vapor adds momentum to vertical motion. It does not create movement from nothing, but it strengthens movement that has already begun. Where rising air contains moisture, that rise can persist longer and extend higher than it otherwise would. This is why moisture makes weather more dynamic. Dry air rises, cools, and often settles back down without much consequence. Moist air rises, cools, releases energy, and can keep rising. The difference lies not in the air itself, but in the invisible energy carried by water vapor within it. This also helps explain why some regions of the world experience more active weather than others. Areas near warm oceans tend to have abundant moisture available. Evaporation loads the atmosphere with water vapor and stored energy. When air rises in these regions, there is more energy waiting to be released. In contrast, dry regions may experience strong heating but limited moisture. Air can still rise, but without much stored energy to reinforce the motion, changes tend to be more restrained. Water vapor also influences horizontal motion. Moist air is slightly less dense than dry air at the same temperature, because water molecules are lighter than the gases they replace. This effect is subtle, but over large areas it can contribute to differences in buoyancy and movement. Despite all this influence, water vapor remains elusive. It cannot be seen directly. It is measured, inferred, and felt only through its effects. Humidity, clouds, and precipitation are signs of its presence. But the vapor itself moves quietly with the air, storing and releasing energy as conditions change. This hidden role is why water vapor is often described as a driver of weather intensity. It adds depth to the system. Temperature differences alone can move air, add moisture, and the same differences can produce much stronger responses. Importantly, this does not mean moisture makes weather unpredictable. The rules remain the same. Energy is absorbed, transported, and released. What changes is the amount of energy involved. The atmosphere becomes more responsive when more energy is available to be released during rising motion. Small disturbances can grow larger. Gentle lifting can become sustained ascent. Patterns that might otherwise fade can persist. This prepares the ground for understanding clouds and storms later on. Clouds are not just collections of droplets. They are visible markers of energy being released. Storms are not sudden outbursts. They are organized responses to stored energy becoming available. None of this happens instantly. Water vapor does not transform the atmosphere overnight. It accumulates gradually through evaporation and is released gradually through condensation. The atmosphere remains a system of slow adjustment, even when the effects become noticeable. There is also a balance at work. As water vapor condenses and energy is released, moisture is removed from the air. Precipitation returns water to the surface, where evaporation can begin again. Energy is absorbed once more and the cycle continues. This cycle links the surface to the sky in a continuous exchange. Oceans feed the atmosphere with moisture and energy. The atmosphere redistributes both. Eventually, water returns to the surface, carrying the system forward without ever breaking its own rules. By recognizing water vapor as stored energy, the atmosphere begins to feel more complete. Air is no longer just moving because of temperature and pressure. It is also carrying energy quietly within it, ready to be released when conditions allow. This hidden energy does not act alone. It works alongside gravity, motion, and rotation. But when it is present, it changes the character of the atmosphere, making responses stronger, deeper, and more persistent. Water vapor may be invisible, but it is never passive. It absorbs energy, transports it, and gives it back at exactly the moments when it matters most. In doing so, it turns simple motion into something more powerful, preparing the atmosphere for the visible structures and evolving patterns that come next. Understanding this role removes another layer of mystery from weather. Intensity does not appear from nowhere. It builds quietly, carried invisibly by water vapour, waiting for the right conditions to release what it has been holding all along. As air moves upward through the atmosphere, something subtle but important begins to happen. The motion itself changes the air, not because it has travelled far, but because of where it has travelled to. Higher in the atmosphere, there is less air above. The weight pressing down is reduced. As rising air enters these regions of lower pressure, it is allowed to expand. The particles that make up the air spread out, occupying a slightly larger volume than before. This expansion has consequences. When air expands, the motion of its particles slows. Not because energy has vanished, but because that energy is now shared across a larger space. The air cools as a result. This process is known as expansion cooling, and it happens to rising air everywhere, every time. No special conditions are required. Air does not need to meet cold surroundings. It does not need to lose heat to something else. Simply rising is enough. As long as pressure decreases with height, expansion cooling follows automatically. At first, this cooling may not produce anything visible. Air can cool significantly while remaining clear. But if the air contains water vapour, cooling eventually reaches a point where the vapour can no longer remain fully mixed in. Water vapour is made of fast-moving molecules, spread invisibly through the air. As the air cools, the average motion of all particles slows, including those water molecules. With less energy, they move less freely. They begin to feel the pull of nearby molecules more strongly. When this happens, water molecules start to gather. Condensation is not a dramatic change. It is a gradual slowing. Molecules that were once moving too quickly to stick together now linger long enough to form tiny clusters. These clusters grow as more molecules join them, creating minute droplets suspended in the air. At this point, motion becomes visible. The air itself has not changed its behaviour. It is still rising, still expanding, still cooling. But the water within it has crossed a threshold. What was once invisible vapour is now present as countless tiny droplets, scattering light and revealing the air's movement. This is how clouds appear, not as objects introduced into the sky, but as markers of where air has cooled enough for condensation to occur. These markers form at specific heights for a reason. Rising air cools at a steady rate as it expands. The amount of water vapour the air can hold decreases steadily as temperature drops. Where those two trends intersect, condensation begins. That intersection often occurs at a particular altitude, determined by the temperature, moisture content, and pressure of the air below. As long as those conditions remain similar, condensation tends to begin at roughly the same height, creating layers rather than random patches. There is nothing accidental about this. The atmosphere is following a set of constraints, and condensation appears where those constraints demand it. Below that level, the air is too warm for condensation to occur. Above it, droplets may continue to form and persist as long as rising motion continues. If the air stops rising, the cooling slows, and condensation may weaken or reverse. This is why clouds do not fill the entire sky from ground to space. They form where rising air cools enough, and they fade where that condition no longer applies. The process is steady rather than sudden. Air does not abruptly turn from clear to cloudy. Condensation begins gradually, often on microscopic particles already present in the air, giving water molecules a place to gather more easily. Over time, enough droplets form to become visible. Throughout this process, energy is being released. As water vapour condenses, the energy it absorbed during evaporation is returned to the surrounding air. This release slightly warms the air, slowing the rate of cooling and influencing how the air continues to rise. But even this energy release follows the same principle of inevitability. It does not reverse the overall cooling caused by expansion. It modifies it. The air still cools as it rises. It simply cools more slowly when moisture is present. Condensation, therefore, does not interrupt atmospheric motion. It accompanies it. What appears as a cloud is not a transformation of air into something new. It is air doing what it always does, with the added detail that part of its motion has crossed a visible threshold. This perspective removes the sense of spectacle. Clouds are not events that arrive. They are conditions made visible. They show where air has risen, expanded, and cooled enough for water vapour to slow and gather. They also reveal structure. Smooth layers indicate widespread gentle lifting. Broken patches suggest uneven motion. Vertical growth hints at sustained rising. None of this requires naming or categorizing. The shapes reflect the motion that created them. Importantly, clouds are not static. They form, change, and dissolve as the balance between rising motion, cooling, and condensation shifts. If air begins to sink, pressure increases, the air compresses, and temperature rises. Droplets evaporate back into vapour, and visibility fades. Nothing dramatic needs to happen for this reversal. A small change in motion is enough. This constant forming and dissolving reinforces the idea that clouds are not objects drifting independently through the sky. They're part of the air itself, appearing and disappearing as conditions allow. From a distance, this can look like transformation. From within the physics of the atmosphere, it is continuity. Cooling through expansion leads naturally to condensation when moisture is present. Condensation makes motion visible. That visibility persists only as long as the underlying conditions remain. This sequence explains why clouds often appear at similar heights across wide areas. It also explains why they can seem to hover in place, even as air flows through them. The droplets form where conditions are right and evaporate where they're not, while the air itself keeps moving. Seen this way, the sky becomes less theatrical and more informative. Each visible patch of condensation is a quiet record of where air has cooled through rising motion. There's also a calm regularity to this process. Rising air cools. Cooling slows molecules. Slower molecules gather. Visibility follows. Nothing is forced. Nothing is added. The system responds to motion in the only way it can. This inevitability is what makes condensation such a reliable feature of the atmosphere. Given moisture and rising motion, it will occur. Remove either, and it will not. By understanding condensation as a consequence rather than a transformation, clouds lose their mystery without losing their interest. They are not signs of instability or drama by default. They are indicators of air doing exactly what physics predicts. This chapter marks a quiet turning point. Until now, much of the atmosphere's behaviour has been invisible. Air has been rising, sinking, spreading, and accelerating without leaving obvious traces. With condensation, motion finally leaves a mark that can be seen. But even now, the emphasis remains on process rather than spectacle. Visibility does not mean disruption. It means conditions have aligned. Cooling air does not decide to form clouds. Condensation does not announce itself. These outcomes unfold naturally, following the same rules that have guided the atmosphere all along. Motion becomes visible not because something new has entered the system, but because something already present has slowed just enough to be seen. And as conditions continue to change, that visibility will fade again, returning the sky to its clearer state, while the air itself continues its quiet, constant motion above the surface. Once condensation makes air motion visible, the shapes that appear in the sky begin to carry information. Clouds are not random decorations. They are temporary structures that reflect how air is moving, how stable it is, and how it responds to being lifted. Some clouds spread out gently, forming wide layers that seem to rest in place. Others build upward, growing taller and more textured as time passes. These differences are not matters of chance. They are clues about the balance of the atmosphere beneath them. To understand why clouds behave differently, It helps to return to the idea of stability. Air is considered stable when it resists vertical motion. In stable conditions, if a parcel of air is nudged upward, it tends to cool, become denser than its surroundings, and sink back toward where it started. The atmosphere, in effect, encourages air to stay where it is. In unstable conditions, the opposite is true. If air is lifted slightly, it cools but remains lighter than the air around it. Instead of sinking back down, it continues to rise. The atmosphere allows motion to build rather than suppressing it. This difference has a direct effect on cloud structure. In stable air, rising motion is limited. Air may lift gently over a wide area, cool enough to condense, and form visible droplets, but further ascent is discouraged. As a result, clouds tend to spread sideways rather than upward. They grow broader, not taller, following the path of least resistance. These spreading clouds indicate that the atmosphere is layered and calm in a vertical sense. Motion still exists, but it is restrained. Air moves more horizontally than vertically, and changes happen slowly. In unstable air, rising motion is encouraged. Once air begins to lift and condense, it remains buoyant. The release of energy from condensation helps sustain the upward movement, allowing the cloud to grow taller over time. These vertically developed clouds signal active motion below. Air is rising persistently, pulling more air upward behind it. The atmosphere is not resisting this movement, it is amplifying it. What matters is not the cloud itself, but what the cloud reveals. Shape becomes a visible map of invisible motion. A cloud that spreads smoothly suggests air that has risen just enough to condense, and then reached a level where further ascent is difficult. The air settles into a layer, flowing outward instead of upward. The structure remains relatively uniform because the motion beneath it is uniform. A cloud that grows upward suggests that rising air continues to find itself lighter than its surroundings. This structure stretches vertically because the motion beneath it is sustained and concentrated. Neither situation is permanent. The atmosphere is always changing, and so are the clouds within it. A stable layer can become less stable as heating increases or as cooler air moves in above. An unstable region can stabilize if rising air removes heat and moisture from below. Because of this, cloud shapes evolve. A spreading layer can thin and fade as motion weakens. A rising structure can slow, flatten, or break apart as conditions shift. Nothing holds its form indefinitely. This impermanence is one of the most important things clouds communicate. They are not fixed objects drifting through the sky. They are processes caught in a visible phase. Even within a single cloud, different motions can be occurring at the same time. Some portions may be rising while others are spreading or sinking. The shape seen from below is the result of countless small adjustments happening simultaneously. This is why clouds rarely look perfectly still, even when they appear to linger. Their edges change, gaps open and close, sections brighten or fade. The air is always moving through them, even if the overall form seems familiar. Cloud structure also reflects how smoothly or unevenly air is rising. When lifting is gentle and widespread, condensation tends to form over large areas at similar heights. The resulting clouds appear smooth and layered, with soft edges and a little vertical variation. When lifting is concentrated into narrower regions, clouds show more texture. Portions rise faster than others, producing uneven shapes that hint at stronger motion below. These differences help explain why some days feel calm despite cloud cover, while others feel more dynamic even before any precipitation appears. The sky is offering clues, quietly, without needing to be dramatic. Stability does not mean inactivity. Even in stable air, motion continues. Air still flows, cools, and warms. It simply does so in a way that discourages large vertical displacements. Energy spreads sideways instead of upward. Instability does not mean chaos. It means the atmosphere is arranged in a way that allows vertical motion to persist. Rising air finds encouragement rather than resistance, and structures can grow taller as a result. Both states are part of the atmosphere's normal behavior. The system shifts between them as energy enters, moves, and leaves. Clouds sit at the boundary between invisible motion and visible outcome. They form where rising air cools enough to condense. Their shape then reflects what happens next. If rising motion weakens, clouds thin and spread. If rising motion strengthens, clouds grow upward. If sinking air intrudes, clouds evaporate and disappear. Each change follows directly from the motion of air beneath and around them. This makes clouds excellent indicators of atmospheric stability. Without naming or classifying them, it is possible to read their structure as a kind of shorthand. Flat suggests restraint. Vertical suggests persistence. Breaking suggests change. Impermanence is central here. Clouds are temporary by nature. They exist only as long as the balance between motion, cooling, and condensation allows them to. Remove any part of that balance, and the structure dissolves. This constant forming and fading is not a flaw. It is the atmosphere adjusting itself in real time. Air rises, releases energy, spreads, sinks, and moves on. The visible traces appear briefly and then vanish, leaving the process intact. This understanding prepares the ground for what comes next. Precipitation does not appear randomly. It emerges from the same processes, extended further. The same rising motion, the same condensation, the same release of energy, all continuing until another threshold is crossed. By learning to interpret cloud structure, it becomes easier to see weather as a continuum rather than a series of events. Nothing suddenly switches from calm to active without passing through intermediate stages. The sky signals what is happening long before anything reaches the ground. Clouds are not messages sent to observers. They are consequences of physics made visible. Their shapes, heights, and lifetimes reflect the stability of the air and the motion beneath them. Watching clouds with this in mind can be quietly absorbing. The sky becomes a slow-moving record of invisible processes, constantly rewritten as conditions change. Some structures spread and fade, others rise and persist. All of them are temporary, and all of them are telling the same story in different ways. The atmosphere is always adjusting. Clouds simply allow that adjustment to be seen for a while, before the air moves on and the sky clears again. When water first condenses in the air, it does not fall. The droplets that form are incredibly small, far lighter than they appear. They are easily held aloft by the gentle upward motion of air and by the natural resistance of the atmosphere itself. For a while, they simply drift, suspended, moving wherever the air carries them. But gravity has not gone anywhere. From the moment those droplets form, gravity is acting on them, just as it acts on everything else. The only question is whether the surrounding air can continue to hold them up. Precipitation begins when that balance slowly shifts. At first, droplets grow by chance encounters. As air moves, droplets collide. Some merge when they meet, forming slightly larger droplets. Others bounce apart or evaporate again. The process is uneven and gradual, guided by motion rather than intention. Larger droplets fall a little faster than smaller ones. As they move downward through the cloud, they may collide with more droplets, growing as they go. Each successful collision adds mass without greatly increasing surface area, making gravity's pull more effective. This is not a rapid process. Most collisions do not result in growth. Many droplets never become large enough to fall, but over time, in regions where droplets are plentiful and motion continues, a few begin to gain an advantage. Eventually some droplets reach a size where the downward pull of gravity outweighs the upward support of the air. When that happens, falling begins. not suddenly and not all at once, but quietly, one droplet at a time. In colder parts of the atmosphere, a slightly different path unfolds. When temperatures are low enough, water vapour may bypass the liquid stage entirely and arrange itself into ice crystals. These crystals grow not by collision at first, but by attracting nearby water vapour, which settles onto their surfaces and freezes. As ice crystals grow, they develop intricate shapes, branching and spreading as molecules attach in specific patterns. These shapes increase surface area, allowing crystals to gather even more vapour as they move through the air. Ice and liquid water often coexist in the same cloud. In these mixed conditions, ice crystals tend to grow at the expense of nearby droplets. Water vapour is more likely to attach to ice, causing droplets to shrink while crystals expand. As ice crystals grow larger, they too begin to fall. Along the way, they may collide with droplets, collecting liquid water that freezes on contact. Or they may merge with other crystals, forming larger structures. What happens next depends on the temperature of the air below. If the air remains cold all the way to the surface, ice stays solid during its descent. If the air becomes warmer, ice may partially or fully melt as it falls. The form that reaches the ground reflects the temperature profile of the air it passed through. This is why falling water takes different forms without requiring different causes. Liquid water reaching the ground has simply remained liquid throughout its descent. Solid forms have remained cold enough to stay frozen. Mixed forms have passed through layers of varying temperature. There is no need for sudden changes or dramatic triggers. The atmosphere provides a vertical path with changing conditions, and falling water responds to those conditions step by step. What all forms of precipitation share is the same underlying story. Particles grow until gravity gains the upper hand. This moment is not violent. It is a quiet threshold. The air has done as much as it can to keep water suspended. Beyond a certain size, the balance tips and descent begins. Once falling starts, it tends to continue. Droplets and crystals pick up speed until air resistance balances gravity again, reaching a steady fall rather than accelerating endlessly. Even then, they remain part of the air's motion, drifting sideways as they descend. Precipitation rarely falls straight down. It moves through the atmosphere along curved paths guided by wind at different levels. What reaches the ground has already travelled a complex route, shaped by layers of motion above. As water leaves the atmosphere, it completes a cycle that began with evaporation. Energy absorbed at the surface was carried upward as vapour. That energy was released during condensation. Now gravity returns the water itself to the surface, ready to absorb energy again. This return is essential. Without it, water would accumulate in the air and deplete the surface. The cycle closes naturally, not through design, but because gravity ensures that nothing stays suspended forever. There is a calm inevitability to this process. Clouds do not hold water indefinitely. Given enough time and motion, some portion of that water will fall. The exact timing varies, but the outcome does not. Precipitation is not an interruption to atmospheric motion. It is part of it. Falling water influences the air it passes through, cooling it slightly and dragging some air downward along the way. These effects are usually gentle, blending into the broader flow. Even light precipitation represents a balance reached rather than a failure. The atmosphere has transported moisture, redistributed energy, and returned water to the surface in the most straightforward way available. This perspective helps remove the sense that precipitation is an event imposed on the atmosphere. It is simply gravity asserting itself once growth has progressed far enough. Some clouds never produce precipitation. Their droplets remain too small, their motion too gentle, or their lifetime too short. Others produce only a brief return of water before dissipating. The atmosphere is selective. not because it chooses, but because conditions vary. Importantly, precipitation does not require intense motion. It can occur in quiet skies as easily as in active ones. The same principles apply in both cases: growth, balance, descent. When water reaches the ground, it does not mark an ending so much as a continuation. Rivers flow, soils absorb, surfaces dry. Evaporation resumes, energy is taken in again, and the atmosphere is quietly resupplied. Seen this way, precipitation becomes one of the most grounded aspects of weather. It is gravity completing its role in a system that has been slowly building toward that moment. No transformation is required. No escalation is necessary. Droplets grow. Crystals form. Gravity acts. The air does not resist this outcome. It allows it. Water that once moved invisibly through the atmosphere returns to the surface, carrying the memory of its journey and the paths it followed and the energy it exchanged along the way. Then the cycle begins again, not abruptly, but steadily, as it always has. Precipitation is not the atmosphere losing control. It is the atmosphere finishing a task it began the moment water first entered the air. In the end, gravity always wins, but it wins patiently, gently, and without spectacle, bringing water home one droplet at a time. Storms are often spoken about as if they arrive suddenly, bringing disruption with them. They are framed as outbursts, as moments when the atmosphere becomes unruly. But when looked at more closely, storms are not departures from normal behavior. They are extensions of it. At their core, storms are systems that manage to keep air rising. That single idea explains almost everything about how they form, how they persist, and how they eventually fade. Rising air is always present in the atmosphere to some degree. Storms appear when that rising motion is able to continue for longer, over a larger area, and with more energy involved than usual. The process begins quietly, just as it does for less dramatic weather. Air near the surface warms and becomes lighter than the air around it. Buoyancy encourages it to rise. As it lifts, it expands and cools, and condensation begins if moisture is present. Up to this point, nothing separates a storm from ordinary cloud formation. The difference lies in what happens next. In many situations, rising air cools enough to lose its buoyancy. It becomes similar in density to the surrounding air and spreads out. Vertical motion weakens, and the system settles into a quieter state. In a storm, that does not happen so easily. As moist air rises and condensation occurs, energy stored in water vapor is released back into the surrounding air. This release does not reverse cooling, but it slows it. The rising air remains warmer, and therefore lighter, than the air around it for longer than it otherwise would. Because of this, the air keeps rising. This sustained buoyancy is the defining feature of a storm. As long as rising air remains lighter than its surroundings, upward motion continues. And as long as upward motion continues, the system remains active. This does not require sudden triggers or explosive beginnings. It requires only that conditions align in a way that allows rising motion to reinforce itself rather than fade away. As air rises steadily, it must be replaced. Near the surface, surrounding air begins to flow inward to fill the space left behind. This inward movement is not aggressive. It is simply air responding to pressure differences created by rising motion above. At the same time, air that has risen high into the atmosphere spreads outward. It cannot keep rising indefinitely, so it flows away at higher levels, completing a circulation within the system. In this way, storms organize themselves into moving loops of air. Air rises, spreads out, sinks, and returns toward the surface, where it can be drawn upward again. This circulation allows the system to persist over time rather than exhausting itself immediately. Importantly, this circulation is not imposed from outside. It forms naturally as a response to sustained rising motion. The atmosphere is not building a storm, It is an accommodating one. Energy continues to flow through the system as long as moisture is available and rising motion persists. Water vapor enters the rising air near the surface, releases energy during condensation, and eventually falls back to the ground as precipitation. The cycle repeats as long as evaporation can resupply moisture from below. Seen this way, storms are not collections of random events. They are organized systems that temporarily maintain an imbalance between energy input and energy release. The imbalance does not mean instability in the everyday sense. It means the atmosphere has found a way to keep redistributing energy without settling immediately into equilibrium. Rising motion continues because the conditions that support it continue. This reframing removes much of the sense of violence often associated with storms. The air is not raging, it is moving efficiently. Even strong winds within storms are part of this organization. Air accelerates where pressure differences are steep, slows where motion spreads out, and curves in response to rotation. Each part of the flow serves a purpose in maintaining the system's structure. There is also a sense of balance within storms. Rising motion is offset by sinking elsewhere. Energy released in one region is carried away by upper-level flow. Precipitation removes moisture, gradually weakening the system. Nothing lasts indefinitely. Storms persist only as long as they can maintain their internal circulation and energy supply. When rising air can no longer stay buoyant, when moisture is depleted, or when surrounding conditions change, the system begins to lose coherence. Upward motion weakens, inflow slows, circulation breaks down into smaller, less organized movements. What remains may still produce clouds or light precipitation, but the defining structure fades. This gradual decay reinforces the idea that storms are not sudden intrusions. They have life cycles shaped by the same physical principles that govern the rest of the atmosphere. There is no single moment when a storm switches on or off. There is only a period when conditions support sustained rising motion, followed by a period when they do not. Understanding storms in this way also explains why they vary so widely. Some systems are brief, maintaining rising motion only for a short time. Others persist longer because moisture, energy, and circulation remain aligned. The atmosphere does not distinguish between ordinary weather and storms. It applies the same rules everywhere. The difference lies in how effectively a particular arrangement of air can keep redistributing energy. This perspective helps remove the idea that storms are inherently unpredictable. While their exact details can be complex, their underlying behavior follows clear logic. Rising air plus moisture plus sustained circulation leads to an organized system. Remove any part of that equation, and the system weakens. It also helps explain why storms tend to move. They're embedded within larger-scale flows that guide their circulation. They do not sit still unless the surrounding atmosphere allows them to. Their paths reflect the broader motion of air across the planet. Even within storms, there is structure rather than chaos. Different regions serve different roles. Some areas focus rising motion. Others allow air to sink. Some carry moisture upward. Others transport energy away. Together, these roles keep the system balanced enough to persist. This balance is delicate but not fragile. Storms can adjust to changes within limits, shifting their internal structure as conditions evolve. But once the imbalance that sustains them fades, the system naturally unwinds. Seen from this angle, storms become less intimidating and more comprehensible. They are not the atmosphere misbehaving. They are the atmosphere doing what it does best when given enough energy and moisture. They represent motion sustained, not motion unleashed. The air is not out of control. It is organized, responding to gravity, energy, and rotation in a way that allows redistribution to continue for a time. Eventually that redistribution succeeds, energy is spread, moisture falls, temperature differences soften, rising motion slows, and the atmosphere returns to quieter patterns, ready to begin the process again when conditions allow. Storms, then, are chapters within the larger story of atmospheric balance. They are not interruptions to that story, but moments when it becomes more visible and more concentrated. By reframing storms as sustained imbalance rather than sudden violence, the atmosphere begins to feel less threatening and more coherent. What once seemed chaotic reveals itself as structured motion, unfolding patiently according to the same principles that have guided the air from the very beginning. Some weather systems develop a stronger vertical character than others. Air does not simply rise and spread out gently. It rises persistently, over greater distances, carrying moisture and energy high into the atmosphere. These systems are not defined by speed or violence, but by depth. The key feature is the updraft. An updraft is simply air moving upward, but in these systems it is sustained and focused. Warm, moist air near the surface continues to rise because it remains lighter than the air around it. Each time it lifts, condensation releases stored energy, helping the air stay buoyant for longer. The result is a column of rising air that can extend high into the atmosphere. This upward motion does not happen in isolation. Surrounding air flows inward near the surface to replace what has risen. Higher up, air spreads outward once it can no longer continue rising. Together, these motions form a vertical circulation that can persist for some time. As air is carried upward, it encounters much colder conditions. Water that began as vapor may condense into droplets, freeze into ice, or shift between forms as it moves through different temperature layers. These changes matter not only for precipitation, but for electrical behavior as well. Within these vertically developed clouds, particles of different sizes and phases move in different ways. Small ice crystals are light and easily carried upward by rising air. Larger droplets or ice pieces are heavier and tend to fall or move downward relative to the updraft. As these particles move past one another, they collide. These collisions are gentle at the scale of the cloud, but they have an important side effect. During contact, electrical charges are transferred. Typically, lighter particles gain one type of charge, while heavier particles gain the opposite. The exact details depend on temperature, particle type, and motion, but the overall result is consistent. Charge begins to separate. Over time, this separation becomes organized. Lighter particles carried upward accumulate charge in the upper regions of the cloud. Heavier particles falling or suspended lower down accumulate the opposite charge. The cloud becomes electrically structured, with different regions holding different charges. This process does not require sudden action or external input. It develops gradually as long as strong vertical motion continues. The updraft maintains separation by keeping lighter particles aloft and allowing heavier ones to remain lower. Meanwhile, the surface below the cloud responds as well. The charged regions overhead influence the distribution of charge on the ground, subtly rearranging it. This happens quietly and invisibly, without any sensation or signal. As charge separation increases and electrical imbalance builds, the atmosphere is normally a poor conductor of electricity, but it is not a perfect insulator. Under the right conditions, it can allow charge to move. When the imbalance becomes strong enough, the air can no longer fully resist it. A sudden movement of charge occurs, travelling through the air along a narrow path. This movement equalizes the difference between regions, at least temporarily. The process happens extremely quickly, but it is not random. It follows the path of least resistance available at that moment. This movement of charge is what is seen as lightning. Lightning is not fire, and it is not an explosion. It is an electrical current passing through air. As the current moves, it heats the surrounding air rapidly, causing it to expand. That rapid expansion produces sound. Thunder is simply the sound of air responding to sudden heating. The air near the electrical path expands faster than the surrounding air can move aside, creating a pressure wave that travels outward. By the time it reaches an observer, it is heard as a rumble or crack, shaped by distance and terrain. There is no added meaning in the sound itself. Thunder does not signal intention or danger. It is a physical response, no different in principle from sound produced by any rapid expansion of air. Because sound travels more slowly than light, thunder is heard after lightning is seen. This delay is a useful reminder that both are part of the same process, unfolding at different speeds. Lightning does not occur continuously within a cloud. It happens in episodes, each one reducing the electrical imbalance that built up. After a discharge, charge separation begins again if the updraft continues and collisions persist. In this way, lightning reflects the internal activity of the system. It appears when vertical motion is strong enough, sustained enough, and complex enough to maintain charge separation over time. Importantly, lightning is not the goal of the system. It is a side effect. The atmosphere is not trying to produce light or sound. It is moving air, transporting moisture, and redistributing energy. Electrical effects emerge because the conditions allow them to, not because they are required. This perspective helps flatten the emotional tone often attached to lightning. It is not a sign that the atmosphere has become aggressive. It is a sign that vertical motion has organized particles in a particular way. The same updrafts that support charge separation also support tall cloud structures and heavy precipitation. These features are linked by shared motion, not by escalation. Thunder, in particular, is often described as threatening, but physically it is simply delayed sound. Its volume and duration depend on distance, the shape of the electrical path, and how sound waves reflect and overlap. A long rumble indicates a long or branching path. A sharp crack indicates a shorter or closer one. Nothing about thunder adds energy to the system. It dissipates energy, spreading it outward as sound waves that quickly fade. Lightning itself also reduces imbalance. Each discharge moves charge, partially resetting the system. Multiple discharges may be needed before vertical motion weakens enough for charge separation to stop. When updrafts weaken, collisions slow. Charge separation becomes less efficient. Electrical activity fades naturally, without needing an external cause. As with other aspects of weather, nothing here is permanent. Vertical motion strengthens, persists, and eventually declines. Electrical effects appear only during a particular window within that life cycle. Understanding lightning in this way removes its sense of mystery without diminishing its interest. It becomes another expression of organized motion, shaped by gravity, temperature, moisture, and the simple behavior of particles moving in air. There is no sudden transformation from ordinary cloud to electrical one. There is a gradual increase in vertical extent, internal motion, and particle interaction. Lightning appears when conditions cross a threshold and disappears when they fall back again. This calm framing matters because it places electrical phenomena back into the broader system. Lightning is not separate from storms. It is not an extra feature layered on top. It is one outcome of sustained vertical circulation. By viewing it this way, the atmosphere remains coherent. Rising air leads to condensation. Condensation releases energy. Sustained motion allows particles to separate charge. Charge moves when imbalance grows large enough, sound follows. Each step follows from the last. There is no need for heightened language to describe this sequence. The processes are already interesting on their own. They are also consistent, repeating wherever similar conditions arise. Vertical storms and electrical charge are not exceptions to atmospheric behavior. They are examples of it operating fully across height, time, and scale. Even lightning, with all its brightness, fits quietly into the story. It is not a break in the system. It is the system responding, efficiently and briefly, before continuing on its way. Some weather systems manage to organize themselves far more completely than others. They persist for days, sometimes weeks, maintaining a clear structure as they move across vast stretches of ocean. These systems are often treated as exceptional, but the processes that sustain them are the same ones already described, simply aligned in a particularly efficient way. At their heart, these systems behave like heat engines. The starting point is warm ocean water. Sunlight steadily warms the surface of the sea, especially in regions where it arrives directly and consistently. Water absorbs and stores this energy efficiently, building up a reservoir of warmth just below the surface. This energy does not stay locked in the ocean. It becomes available to the atmosphere through evaporation. As warm, moist air rises from the ocean surface, it carries stored energy upward in the form of water vapor. When that vapor condenses, energy is released back into the air, keeping the rising motion going. This continuous supply of warmth from below allows the system to maintain sustained upward motion over a wide area. Rotation plays a crucial role at this stage. Because the Earth is rotating, air flowing toward the region of rising motion does not move straight inward. Instead, it curves. This curvature prevents air from rushing directly into the center and stopping. Instead, the flow begins to circulate around the region of lowest pressure. As this circulation strengthens, it becomes more organized. Air spirals inward near the surface, rises near the center, spreads outward at higher levels, and then sinks farther away before returning again. The system closes in on itself, forming a self-sustaining loop of motion. Rotation does not create the storm, it refines it. Without rotation, rising air would still occur over warm water, but the system would struggle to organize. Rotation allows motion to persist without collapsing inward, spreading energy smoothly around a central region, instead of exhausting it all at once. As the circulation tightens, pressure at the center drops further. Lower pressure encourages more air to flow inward near the surface, drawing in additional warm, moist air from the ocean. This inflow feeds the rising motion, which releases more energy, which strengthens the circulation in return. This feedback is what allows the system to grow. Importantly, this growth is not unlimited. It depends entirely on continued access to warm ocean water. The system does not generate energy on its own. It converts energy that already exists, drawn steadily from the sea below. This is why these systems weaken when they move over cooler water or over land. The energy source is reduced or removed. Evaporation slows. Rising air loses its reinforcement. The circulation begins to decay. Within a fully developed system, the structure becomes remarkably symmetrical. Air spirals inward in bands, rising most strongly near the center. At high altitude, air spreads outward in all directions, forming a broad outflow that balances the inward motion below. This symmetry is not aesthetic, it is functional. It allows energy and mass to move efficiently through the system. At the very center, something different happens. As air spirals inward, it eventually reaches a point where it can no longer keep rising. The circulation becomes so organized that sinking motion develops at the core. Air descends gently, warming as it compresses, creating a relatively calm and clear region. This central sinking zone is not a gap in the system, it is part of the balance. Rising air must be matched by sinking air somewhere, and in a highly organized circulation, that sinking becomes concentrated at the center. The surrounding region, where rising motion is strongest, contains the most active condensation and energy release. This contrast between rising motion around the center and sinking motion within it creates the distinct structure that makes these systems easy to recognize. Despite their appearance, these systems are not rigid. Their symmetry is maintained only as long as conditions allow. Changes in surrounding winds, variations in ocean temperature, or interactions with land can distort the circulation, weakening it or pulling it apart. There are also natural limits to how strong these systems can become. As wind speeds increase near the surface, they enhance evaporation, which supplies more energy. But those same winds also stir the ocean, bringing cooler water up from below. This cooling reduces the temperature difference that fuels evaporation, placing a natural cap on intensity. In addition, very strong winds increase friction at the surface and within the atmosphere, dissipating energy as heat. The faster the air moves, the more energy is lost through resistance. This too limits growth. The atmosphere is not inclined to run away with itself. It builds structure until opposing effects balance the inputs. Because these systems depend so strongly on their energy source, they are sensitive to their environment. A small change in ocean temperature or atmospheric structure can alter their behavior significantly. Strengthening and weakening are part of their normal life cycle. What makes these systems especially memorable is not that they are different, but that they display atmospheric processes so clearly. Rising motion, condensation, rotation, and circulation are all present in a highly organized form. They are not exceptions to the rules of weather. They are demonstrations of those rules operating efficiently over large scales. Seen this way, there is no need to frame them as uncontrollable forces. They are constrained by physics at every step. They form only under specific conditions. They persist only while energy continues to flow, and they decay when that flow is interrupted. Their movement across the ocean reflects the larger currents of the atmosphere that guide them. They do not wander at random. They follow paths shaped by global circulation and upper-level winds, changing direction only when those guiding flows change. Even their eventual dissipation is orderly. As energy input fades, rising motion weakens. Pressure rises at the center. Circulation slows. The system loses its symmetry and blends back into the broader atmosphere. Nothing collapses suddenly. The structure relaxes. Understanding these systems as heat engines helps remove much of the mystery that surrounds them. Warm water supplies energy. Rising air converts that energy into motion. Rotation organizes the flow. Limits emerge naturally from friction and cooling. There is also a certain simplicity in this view. No special ingredients are required. No hidden forces appear. The same processes described throughout the atmosphere are simply aligned in a way that allows them to reinforce one another for a time. These systems are impressive not because they break the rules, but because they follow them so well. They show how the atmosphere can organize itself when energy is abundant and motion is allowed to persist. They also show how that organization always remains temporary, shaped by boundaries that cannot be crossed. In the end, these storms are not monsters roaming the ocean. They are structured responses to warmth, moisture, and rotation, operating within clear limits, and fading when those limits are reached. Seen through this lens, they become less frightening and more intelligible. Powerful, yes, but also predictable in their behavior and finite in their lifespan. They rise, organize, persist, and decay, all as part of the atmosphere's ongoing effort to move energy from where it is plentiful to where it is not. And once that task is complete, the system lets go, returning its air to the wider circulation, leaving only cooling water behind and a quieter sky above. Weather systems span a wide range of sizes. Some stretch across oceans, others across continents. A few, however, exist on a much smaller scale, confined to narrow regions where motion becomes unusually concentrated. These systems are brief, local, and highly specific in the conditions they require. What distinguishes them is not raw power but focus. Near the surface, the atmosphere behaves differently than it does higher up. Air is slowed by friction with the ground, buildings, vegetation, and terrain. Temperature and pressure can change sharply over short distances. Winds may differ dramatically from one field to the next. This creates an environment where strong gradients can form close together. A gradient is simply a difference across space. When temperature, pressure, or wind speed changes rapidly over a short distance, the gradient is steep. Most of the time, these gradients are modest and spread out. Occasionally, they become compressed into very small areas. When that happens, motion can become tightly organized. In certain situations, air near the surface begins to rotate gently as part of a broader circulation. This rotation is usually weak and spread out, covering a large area with little noticeable effect. On its own, it does not lead to anything unusual. The key change occurs when this rotating air becomes concentrated. If strong rising motion develops nearby, air is drawn inward toward the region of ascent. As air flows inward, any existing rotation is tightened. The same amount of rotational motion is now confined to a smaller space. As a result, rotation speeds up, not because energy was added, but because motion was compressed. This process is similar to narrowing a stream. The water flows faster through the tighter channel, even though the overall amount of water has not changed. In the atmosphere, narrowing the region of rotation increases its intensity. This tightening happens close to the surface, where gradients are already steep and motion is constrained by friction. The result can be a narrow column of rapidly rotating air extending downward from a region of strong upward motion. This column does not form suddenly. It develops as the balance between inflow, rotation, and rising motion aligns briefly in the right way. Many such alignments begin and fade without producing anything noticeable. Only a small fraction become organized enough to persist for more than a short time. Duration is one of the defining features here. These systems are short-lived. They exist on timescales of minutes rather than hours or days. Their structure depends on a precise arrangement of motion that is difficult to maintain. Small changes in wind, temperature, or pressure can disrupt the balance and cause the rotation to weaken or break apart. Because of this, they are rare. Even in regions where conditions are favorable, most storms do not produce them. The atmosphere usually finds easier ways to redistribute energy without concentrating motion so tightly. When they do form, their scale remains limited. The rotating region is narrow compared to larger weather systems. The surrounding atmosphere may be relatively calm, with only subtle signs of the intense motion occurring within a small area. This contrast in scale is important. While the rotation itself may be fast, the amount of air involved is small. The system does not dominate the surrounding weather. It is embedded within it, drawing briefly on the motion and energy already present. The air within this rotating column follows curved paths, spiraling around a central axis while also moving upward. This combination of rotation and ascent links it to the larger storm system above, but the near-surface environment plays a critical role in shaping its behavior. Surface friction slows air unevenly, creating differences in speed and direction over short distances. These differences help sharpen rotation when air converges. At the same time, friction limits how long the structure can remain coherent. As with other atmospheric phenomena, gravity remains present throughout. Air continues to rise and sink according to buoyancy and pressure differences. The rotating motion is layered on top of these vertical movements, not separate from them. There is no requirement for extreme instability or widespread chaos. What matters is the alignment of motion at multiple levels, allowing rotation to be focused rather than dispersed. Because the structure is narrow and short-lived, its effects are highly localized. Areas only a short distance away may experience little more than shifting winds or passing rain. The broader storm continues its evolution largely unaffected. This limited reach reinforces the idea that these systems are not a different category of weather, but a specialized outcome within a familiar framework. They represent an extreme end of a continuum, not a break from it. Their brief lifespan also reflects the atmosphere's tendency toward balance. Concentrated motion is inherently unstable. It dissipates quickly as air mixes, pressure equalizes, and gradients soften. The system unwinds, returning its energy and momentum to the surrounding flow. There is no build-up toward permanence. These systems do not grow steadily over long periods. They appear when conditions align and disappear when those conditions shift, often leaving little trace behind. This transience is a defining feature. It explains both their rarity and their unpredictability in precise timing and location. The atmosphere does not aim to produce them. It occasionally allows them as a byproduct of broader motion. Understanding this helps remove the sense that they are inevitable or widespread. They require a narrow set of circumstances, occurring at the right place and time. Most storms never approach that configuration. It also helps place them in context alongside larger systems. Compared to ocean-spanning circulations or continent-scale patterns, these rotating columns are small adjustments, brief moments when motion is unusually concentrated rather than evenly distributed. From a physical perspective, there is nothing fundamentally new happening here. Air is moving from higher pressure to lower pressure. Rotation is tightening due to convergence. Rising motion is sustained by buoyancy and energy release. Gravity, friction, and resistance continue to act throughout. The difference lies in scale. By contrasting these systems with larger, longer-lived phenomena, it becomes clear that intensity does not always correlate with size or duration. The atmosphere can express energy gently over wide areas or sharply within narrow ones, depending on how motion is arranged. These concentrated systems remind us that weather operates across many scales at once. Broad patterns set the stage. Local conditions refine the outcome. Occasionally, that refinement becomes extreme for a short time. When the alignment ends, the system relaxes, rotation slows, gradients weaken, air resumes a more diffuse flow, the atmosphere absorbs the disturbance and continues its broader circulation. There is no lasting disruption. The balance reasserts itself quickly. By viewing these events as brief expressions of concentrated motion rather than dramatic anomalies, they become easier to understand. They are rare, short-lived, and tightly constrained by their environment. They do not redefine the atmosphere. They momentarily highlight how focused motion can become when gradients sharpen and flows align. In the wider context of weather, they are small, fleeting details within a vast, continuously adjusting system, appearing briefly, doing their work, and then dissolving back into the surrounding air without ceremony. As temperatures fall, the atmosphere begins to behave differently. Motion slows, energy moves less freely. Processes that once favoured rising air and rapid change begin to favour settling, layering, and accumulation instead. Cold-dominated weather is not driven by bursts of energy. It is shaped by restraint. When air cools, the motion of its particles decreases. Expansion becomes less likely. Buoyancy weakens. Instead of rising easily, air tends to remain close to the surface, spreading out rather than lifting upward. Vertical motion still occurs, but it is limited and often gentle. This creates an atmosphere that feels quieter, both physically and perceptually. Freezing processes begin when temperatures drop low enough for water to change state. As before, nothing abrupt is required. Molecules simply lose enough energy that they can no longer remain in a liquid arrangement. They settle into more rigid structures, locking together rather than flowing freely. When condensation occurs in cold air, the resulting particles may freeze almost immediately. Water vapour can attach directly to ice surfaces, building solid structures molecule by molecule. The result is precipitation that forms slowly and delicately, shaped by temperature rather than force. Snow forms through this gradual assembly. Ice crystals grow as water vapour settles onto them, expanding outward in structured patterns. Their shapes reflect the conditions they pass through, including temperature and humidity, but the process itself is calm. Growth is steady, guided by diffusion rather than collision. Because snow forms in cold, relatively stable air, it often falls gently. The flakes are light, offering a large surface area relative to their mass. Air resistance slows their descent, allowing them to drift and settle rather than strike the ground. Accumulation becomes the defining feature here. Snow does not rush. It arrives slowly and remains where it falls, building layer upon layer. Each addition slightly alters the surface below, reflecting light differently, insulating the ground and reducing further motion. Other forms of frozen precipitation arise when temperature varies with height. If ice crystals fall through a layer of warmer air, they may partially melt, becoming droplets. If those droplets then pass through colder air again before reaching the surface, they may refreeze into small pellets. These pellets are denser and fall more directly than snow, bouncing lightly on contact rather than spreading. In situations where liquid droplets fall through cold air near the surface without refreezing beforehand, a different outcome occurs. The droplets remain liquid until they make contact with objects that are below freezing. Upon contact, they freeze almost instantly, forming a smooth coating. Each of these outcomes reflects the same principle. Falling water responds continuously to the temperatures it encounters. There is no need for separate mechanisms or sudden shifts. The structure of the precipitation mirrors the structure of the atmosphere it passes through. Cold air also tends to suppress vertical mixing. Warmer air near the surface does not rise as easily when capped by colder layers above. This encourages stratification, where air layers remain stacked rather than blended. In these conditions, clouds often form in broad uniform sheets rather than towering structures. Motion within them is subtle. Condensation continues, but without the sustained rising motion that leads to rapid growth or heavy precipitation. The pace of weather slows accordingly. Instead of dramatic changes over short periods, cold-dominated weather often persists. Temperatures remain steady. Cloud cover lingers. Light precipitation may continue for hours, quietly adding to what is already there. Energy release is limited. With little moisture evaporating and less condensation occurring, the atmosphere has fewer opportunities to redistribute heat quickly. The system settles into a low-energy state. This stillness has physical consequences. Snow-covered surfaces reflect more sunlight, reducing further warming. Ice-covered ground limits evaporation. Cold air pools in low areas, reinforcing temperature differences near the surface, while leaving upper layers relatively unchanged. These feedbacks promote stability rather than motion. The atmosphere becomes resistant to disturbance, requiring significant energy input to change its state. Even wind behaves differently in cold conditions. With reduced vertical mixing, winds near the surface may be light or intermittent, while stronger flow passes overhead without reaching the ground. When wind does occur, it often feels sharp rather than forceful, shaped by temperature contrast rather than pressure imbalance. Sound travels differently as well. Cold air can bend sound waves back toward the surface, making distant noises seem closer. This contributes to the quiet intensity often associated with cold weather, even though the atmosphere itself is simply more orderly. Accumulation becomes the central theme. Snow gathers on horizontal surfaces, smoothing edges and softening outlines. Ice coats branches, wires and roads, adding weight without motion. Each addition remains until external conditions change, not because it is active, but because nothing removes it. This persistence contrasts strongly with warm weather precipitation, which tends to run off or evaporate quickly. In cold conditions, water stays where it lands, reinforcing the sense of pause. Over time, accumulated snow and ice influence the atmosphere above them. They cool the air near the surface, strengthen temperature inversions, and further reduce vertical exchange. The system becomes increasingly self-reinforcing. Despite this stillness, the atmosphere is not inactive. Processes continue at a slower pace. Water vapor still moves, heat still flows, gravity still acts. The system has simply shifted into a mode where changes are incremental rather than expressive. Cold-dominated weather also highlights how sensitive atmospheric behavior is to temperature. A difference of only a few degrees can determine whether precipitation drifts down gently, bounces briefly, or coats surfaces silently. These differences matter structurally, not emotionally. They shape surfaces, alter traction, affect insulation, and influence how energy is stored and released over time. Importantly, cold weather does not represent an absence of weather. It represents a different balance. Energy input is reduced, motion is constrained, vertical exchange is limited. The atmosphere responds by settling rather than circulating vigorously. This balance can persist for long periods, especially in regions far from strong heat sources. The atmosphere becomes predictable in its quietness, even as small variations continue within it. Eventually conditions change, sunlight strengthens, warmer air arrives, accumulated ice and snow begin to melt. Energy returns to the system and motion increases again. But until then, cold-dominated weather remains defined by patience. Nothing rushes, nothing escalates. Processes unfold slowly, building layer upon layer without drawing attention to themselves. By understanding freezing, accumulation, and structural differences in cold precipitation, weather becomes easier to read during these quieter periods. What appears still is simply balanced. What seems inactive is carefully arranged. Cold weather is the atmosphere resting within its constraints, conserving energy and allowing gravity, temperature, and structure to guide outcomes gently and consistently. It is not an interruption in the story of weather, but a slower chapter within it, written in layers rather than motion, and measured in accumulation rather than speed. Weather does not begin and end in episodes. It does not switch on with a storm or switch off when the sky clears. It continues quietly, adjusting moment by moment, whether it is noticed or not. Even on the calmest day, air is moving. Heat is being absorbed, transported, and released. Water is evaporating and condensing. Pressure differences are forming and dissolving. The atmosphere is always in motion, even when that motion is subtle enough to feel like stillness. This continuity becomes clearer when time is allowed to stretch. Over the course of a single day, sunlight warms some regions more than others. Air responds. Over the course of months, the angle of sunlight changes, shifting where energy enters the atmosphere most strongly. Over the course of a year, these shifts repeat, tracing a slow and predictable pattern. This is what seasons are made of. They are not moods of the planet, and they are not driven by distance from the sun. They arise from geometry and time. The Earth is tilted as it moves around the sun, which means different regions receive sunlight at different angles throughout the year. When sunlight arrives more directly, energy is concentrated. When it arrives at a shallow angle, energy is spread out. The atmosphere responds to these changes continuously. During periods of stronger heating, air warms more easily, moisture increases and rising motion becomes more common. During periods of weaker heating, cooling dominates, vertical motion slows, and accumulation replaces circulation. The familiar patterns of warm and cold seasons emerge naturally from this shifting balance. Nothing about this process is abrupt. There is no single moment when one season becomes another. The atmosphere transitions gradually, carrying traces of one state into the next. Late warmth lingers into cooler months. Cold air persists even as sunlight strengthens again. This overlap reinforces the idea that weather is not a sequence of isolated events. It is a flow. The same principles apply across all scales. A gentle breeze and a large storm both arise from air responding to pressure differences. A drifting cloud and a towering system both reflect rising motion and condensation. Snowfall and rainfall both complete the same water cycle under different thermal conditions. The atmosphere does not change its rules. It applies them everywhere, all the time. At the center of everything is energy imbalance. Sunlight does not heat the Earth evenly. Some regions receive more energy than they lose. Others lose more than they gain. The atmosphere exists largely to reduce these differences, transporting heat and moisture from where they are abundant to where they are scarce. Air moves because of this imbalance. Water changes state because of it. Winds curve, clouds form, and precipitation falls as part of the same effort to redistribute energy. Even rotation, which adds complexity, does not replace this goal. It shapes the paths air takes, organizing motion into curves and loops. But the underlying reason for movement remains the same. Energy is unevenly distributed and the atmosphere responds. This response never finishes. Even when differences are reduced locally, they reappear elsewhere. Night follows day. Seasons progress. Land cools faster than water. Ice reflects sunlight. Warm air rises, cool air sinks. Each adjustment creates new imbalances that require further adjustment. Weather, in this sense, is the atmosphere thinking out loud. It explores the consequences of geometry, rotation, gravity, and heat in real time. It tests configurations, relaxes them, and moves on without memory or intention, yet with remarkable consistency. Understanding this continuity helps dissolve the idea that weather is something that happens to the atmosphere. Weather is what the atmosphere is doing at every moment. Clear skies are not the absence of weather. They are weather in a low-energy state. Calm air is not inactive air. It is air whose movements are small and evenly distributed. Likewise, active systems are not disruptions. They are efficient responses to strong imbalances that cannot be resolved gently. Seen this way, the atmosphere becomes less dramatic and more coherent. Storms are not interruptions. Cold spells are not failures. Heat waves are not moods. Each reflects the same processes operating under different conditions. This perspective also highlights why prediction has limits. The atmosphere is continuous and interconnected. Small differences can grow or fade depending on how they interact with larger patterns. Precision becomes difficult not because the system is random, but because it is responsive at many scales at once. Despite this complexity, the broad patterns remain steady. Warm air tends to rise, cold air tends to sink. Moisture carries energy, rotation curves motion. Gravity pulls everything downward. These tendencies do not change. The atmosphere never forgets them. Every chapter of weather, from the quietest frost to the most organized circulation, fits within this framework. The details vary, but the structure remains familiar. As seasons turn, the emphasis shifts. Some processes become more prominent, others recede, but nothing disappears entirely. Even in the depths of cold-dominated weather, energy continues to move. Even in the height of warm seasons, stability returns eventually. This continuity is what allows weather to feel both familiar and endlessly variable. The same sky produces endless combinations, not by reinventing itself, but by recombining the same elements under slightly different conditions. There is also comfort in this repetition. The atmosphere does not surprise itself. It responds according to rules that have held for as long as air has surrounded the planet. The patterns observed today are echoes of patterns that have played out countless times before. Even when weather feels unusual, it remains grounded in the same physics. Extremes are extensions, not exceptions. They reflect stronger imbalances or more efficient organization, not new behavior. By tying everything back to energy imbalance, the atmosphere becomes easier to hold in mind. Weather is not a collection of names or events. It is a process unfolding continuously, guided by simple principles applied at immense scale. Nothing truly stops. Motion slows, speeds up, redirects and reorganizes, but it never ceases. The air above the surface is always adjusting, always responding, always in conversation with the energy moving through it. This is why there is no final moment in weather, only transitions. One system fades into another. One season gives way to the next. One pattern dissolves as another takes shape. The atmosphere remains active throughout, even when its activity is barely perceptible. Understanding weather in this way invites a quieter kind of attention. Instead of watching for events, it becomes possible to notice processes. Instead of waiting for changes, it becomes possible to recognize continuity. The sky is never blank. It is always telling the same story, written at different speeds and scales shaped by sunlight, water, air, and time. Weather never stops because the conditions that create it never settle completely. Energy continues to arrive, the planet continues to turn, gravity continues to act, the atmosphere continues to respond. And in that response, endlessly repeated and endlessly varied, the familiar patterns of weather continue to unfold, not as interruptions to the world below, but as one of its most constant and reliable processes. The sky above is always active, even when it looks calm. Air continues to move, temperatures continue to adjust, and moisture continues to shift between invisible and visible forms. These processes never stop. They simply become quieter or more noticeable depending on conditions. This constant motion is not disorder. It is the atmosphere responding to uneven energy. Sunlight does not warm the planet evenly. Day and night alternate. Seasons shift. Land and water heat and cool at different rates. As long as these differences exist, the atmosphere will keep moving air and moisture to reduce them. That work is never fully finished because the inputs never stop. What changes is not whether the atmosphere moves, but how. Sometimes motion is spread out and gentle. At other times it becomes organized and more obvious. Both states follow the same rules. Warm air rises, cool air settles. Moisture carries energy and releases it when conditions allow. Gravity returns water to the surface. Rotation shapes the paths air takes. Because these rules do not change, weather remains understandable beneath its variety. Patterns repeat. Systems form and fade within clear limits. Even strong events are not departures from balance, but efficient ways of restoring it. Clear skies are not the absence of weather. They are weather in a low-energy state. Calm air is not inactive air. It is air whose movements are small and evenly distributed. Weather does not aim for a final state. There is no moment when balance is complete and motion stops. As long as energy continues to arrive and leave the planet, the atmosphere will keep adjusting. This adjustment is steady, not urgent. One pattern eases into another. One season gives way to the next. Nothing needs to happen suddenly. The sky above continues its work whether it is noticed or not. It follows the same constraints it always has, quietly and consistently. Weather never stops, but it does not need attention to continue. And knowing that, it becomes easier to let the atmosphere move on its own, while everything below is free to slow down.